All right, we're going to be looking at the integral test, and it's just a test for certain conditions are met. We can determine if our series is converging or diverging. And so we're going to start with divergent. And so we have 1 over n here. This is our series, and this is a divergent series, and we're going to show you why right now. Well, I'm going to. So if you look at this sum from n equals 1 of 1 over n to infinity, you can think of it as a Riemann sum from left hand. So if we were to plug that in, we would get sum n equals 1 to infinity of 1 over n is 1 over 1, 1 over 2, plus 1 over 3. So it's just our function. Our f of n is 1 over n. And you just keep plugging that in. So what it's giving us is our heights. That's 1, that's a half, that's 1/3, 1/4, 1/5, and so on. So as we move off to infinity. And so if you look at that, our delta x here is 1 with a 1. So we can say that this is our sum, is this Riemann sum with left endpoints. And what we are doing is overestimating excuse me there, I don't know what happened there. Let's try that again. We are overestimating our integral right there. So that's our area that we would normally be finding with the integral, and you can see that those little pieces right here are more. And so we can make this statement here, that our sum from n equals 1 to n equals 1 to infinity of 1 over n is bigger than our integral. So if we can show that the integral diverges, well, then our sum itself also has to diverge as long as these little pieces stay above. So as long as we're always decreasing here, our left hand will always be an overestimate, and that's one of the conditions. So let's show this is true. So we know that the integral from 1 to infinity of our 1 over x dx is equal to the limit as t approaches infinity, 1 to t, of 1 over x dx. And then we know that is the limit as t approaches infinity of, sorry, it's not 1 over, it's ln of x from t to 1. So if we plug that in, we get the limit as t approaches infinity. And this should look very familiar. It's from 7.8. It's our indefinite integrals. And we did this one already. And we showed that this becomes infinity. So it diverges. And since our sum is less than this, then what we're getting is that our sum from n equals 1 to infinity of 1 over n is less than our integral from 1 to infinity of 1 over x dx, which is greater than, well, sorry, not greater than, equal to infinity. And so obviously 1 over n can't be bigger than infinity, which means the sum from n equals 1 to infinity of 1 over n is infinity. So it diverges as well. So what this is saying is as long as our integral diverges, our sum's going to diverge as well, as long as we get some conditions that are met. At the very end, I will explain this on what those conditions are. Let's look at converging. So if we modify it with that same basic idea, we can now say from right endpoints, we are underestimated. So since our function's decreasing, always here, our right endpoints are what we can use. So if you go back up here, that right there was our left, and you can see that it's overestimating. And here we're using right, and it's underestimating. Here's the issue that we have. So if you look here, if we plug in 1, right, sum of n equals 1 to infinity of 1 over n squared, that's the sum we're trying to show it diverges or converges, we would get 1 over 1 plus 1 over 2 squared plus 1 over 3 squared plus 1 over, and so on, all the way down. But see, this is not from plugging in 1, it's from plugging in 2. So we would end up with 1 over 2 squared, 1 over 3 squared, 1 over 4 squared, and so on as we move down it. And so all we have to do is basically add that a sub 1 in there. So I'm saying that the sum from n equals 1 to infinity of 1 over n squared minus 1 now, because that's our first term, that would give us our sum from n equals 2 to infinity of 1 over n squared. So that's all that is, and that would give us our left. So if you notice that now this is in underestimate. So if it's an underestimate, then as long as our integral converges, everything below it will also converge. It's kind of like the squeeze theorem. In fact, it's similar to what we were dealing with here. So if we can now show that the limit as, well, let's write it exactly the way we have it from before, integral from 1 to infinity of 1 over n squared dx, if we can show that that converges, then that would mean that our series also converges. And this is our integral test. And again, it needs to stay that it's decreasing here so that it's always an underestimate. Okay. So we end up saying the limit as t approaches infinity of the integral from 1 to t, 1 over, I got to change that to an x, sorry. That's an x squared dx. 1 over x squared dx. And so now when we take the integral, we can rewrite this as x to the negative 2. And so then you're going to add 1, so it's x to the negative 1, and then a negative. And then now we can put t and 1, and I don't have room for the limit, so I'm just going to move that over here. We'll put the equals here. Limit as t approaches infinity. So now we get limit as t approaches infinity, and I'm going to rewrite as a fraction, negative 1 over t. And then plugging in the 1, so that's plus 1. And you can see now that this goes to 0. And so we would end up with 1. Well, now that means that this right here, right, sum from n equals 1 to infinity of 1 over n squared minus 1, right, is less than 1. So I can add that 1 over. Oops, forgot the 1 over n minus n squared is less than 2, which means it converges. So if this is converging to 2, then anything less than it also has to converge it. It's bounded. So it's decreasing right here. And there you go. So this is our integral test. So given f is continuous, we need it to be continuous, positive, and decreasing. That way we get that under an overestimate. And on some interval from start off to infinity, and we let a of n equals f of n, normal stuff. Then our integral, if the integral converges, well, our sum converges. If our integral diverges, our sum diverges. And we don't have to think about this as just 1. It's just the starting value. So you can see I have this here. It doesn't really matter. If I move this to the right and I start it at a different value like 5, it's still overestimating, right? And so if it's converging way back here at 1, it's going to converge way over here at 2. Sorry, that's a diverge. And we could do the same thing here with converging. So if I move this over, you can see we're now starting at different values, but it's still underestimating. So it's really just a starting value. Here it's 4. So if you can show that our function f, that's that basic a sub n, is continuous, positive, and decreasing, then we can take the integral, and if it converges, our series converges, and if our integral diverges, our series diverges as well. That's all it's showing us, is if it converges or diverges.